Okay, so last time we defined vector space or the field F K, which is where V is an abelian group under so-called addition operation, where scalar multiplication we multiply by vectors by scalars. Scalars are just elements of the field K. And third condition, these operations are compatible in this following sense. The two operations are compatible. What we mean is this: for all vectors UV in V and scalars lambda mu in K, we have lambda plus mu times V is just lambda V plus mu V. So scalar condition distribute over multiplication, and we have this. So scalar multiplication distributes over vector addition. 1 times V is always V, and 0 times V is always 0. These two zeros are different. This is the zero element of the field K. This is the zero element of the vector space V. The identity element of the abelian operation, this operation, the identity element of the vector operation for vector space. But here, this is the element of the field K. So 0 times the scalar 0 times any vector is the 0 vector. Okay, and here scalar 1 of the field times any vector is equal to the vector itself. So multiplying it with identity element of the field acts as identity. All right. Now, I guess this was the place I stopped last time.
Can I explain one more time the first operation? And he gave as an example.
This one?
Yeah.
So this means V is an abelian group. There is an operation with respect to this operation. V is an abelian group. Okay.
And then the next is plus.
Oh, here this is just a notation. This operation takes two vectors, let's say U and V, and maps them to this. So it's just a notation. So whenever you take two vectors, you can add them up. Okay.
And then the between them is not multiplication.
Plus, this is plus. Right. We don't multiply vectors with each other. There are special cases where we multiply vectors, but that's not a part of the being a vector space. We have multiplication in some special vector spaces. Multiplication of vectors. We have in R2, this is the usual cross product of vectors. We have something similar in R7, also in R2 and R4, but basically these are all, okay? We don't have any other actually vector spaces where we can multiply vectors. That's a recent result. It is only proved in 60s, 50s, and 60s using actually topology, algebraic topology. That these are the only vector spaces basically which admits vector multiplication. Okay, so maybe I should vector products occur, exist only in some special cases. And this is true. Increase and decrease using algebraic mechanism. So I didn't tell you the exact statement, but if you look for products like vector product in R3, it doesn't exist in general. There is a similar product. So here we have, remember, we have RJ case, right? I times J is K and so on. This vector product. There is something special, there is something similar to that in R7, and that's it, okay? What? In R7? R2. Well, you may consider this as complex numbers, and complex numbers you can multiply, and this is quaternions. We have 1, R, J, K. I'll talk about them. Okay, I'll talk about them. The thing is that, you know, even such a simple looking question has actually a difficult answer. You know, why cross product in R3 doesn't generalize to all dimensions. Okay, that's a naive question, but answer is not simple. Okay, it's only proved recently, and people looked for such things for many years. Of course, they couldn't find because it doesn't exist. Okay. Okay. Let's talk about some examples of vector spaces. Okay. Yeah, first example is zero example. Vectors in the free space R3. This is a vector space over R. This is the vector space for R. How? Well, so V is that R3, okay, meaning that this is a set of triples like this, like x1, x2, x3, x are real numbers. The first condition was that there should be an addition operation on this set. So the addition operation is this. So this plus operation. If we have two vectors, this one and let's say this one, how do you add these two vectors? Well, you just add component wise, right? This is something you know from high school. We know how to add two vectors in R2, right? So this is the vector addition. What about scalar multiplication? Whenever you take a scalar, so this is our field, okay? So this is our field, okay? And a vector, let's say x1, x2, x3. So what is lambda times v? Well, lambda times x1, x2, x3. This is defined as just, you just multiply each component by lambda. So lambda times x1, right? Lambda times x2, lambda times x3. These are the definitions, okay? This is how we add two vectors. When I write, an equality sign and a dot above it, it means this is the definition. Definition of two vectors is given by this formula. Definition of the scalar product of a vector v by a scalar lambda is like this. Actually, I should put it here. So this multiplication lambda times v is just this gadget. Okay, this is the definition. Vektörleri skalarla çarpmayı böyle tarif ediyoruz. Then we should do what? We should check that these operations are compatible. Let's do that. Okay. So, what is the first thing we need to check? This times b. So lambda plus mu times b. x1, x2, x2. Okay, now what is this? Well, by definition, this is just, you take this scalar and multiply by each entry. This product, of course, this product here is the product of two real numbers. We know how to multiply two real numbers, right? This is a real number. Elements of the components of the vector are real numbers. And I know how to multiply two real numbers. But till I defined this, I didn't know how I would multiply a vector by a real number. And this is my definition. And now I want to check that my definitions are compatible in the sense of this condition 3. Okay, now what is this? Well, two real numbers added up, multiplied with a third real number. We know that real numbers is a field, therefore I can just write this as follows. This is lambda times x1 plus mu times x1, right? This is the property of real numbers. And then similarly, this is lambda times x2 plus mu times x2, and this is lambda times x3 plus mu times x3. Okay. And then I do what? Well, I use my definition of vector summation. Well, this vector is nothing but the sum of these two vectors, right? Right? How would you sum these two vectors? You just sum components, right? And then, so this is the definition of vector addition. And then I use the definition of vector, scalar product. This vector is nothing but lambda times the vector x1, x2, x3. And this is nothing but mu times x1, x2, x3. Okay. So this is just lambda times v plus mu times v. So this is just the first property I stated here. Okay. Pardon. So it is the first property I stated over here. Okay. We have to, of course, check all of these. Let me just do it for the sake of completeness. I will not do in this much detail later, but let me just do this one. What else should I check? I should check the following. For any lambda and vectors, let's say x1, x2, x3, and a third vector, let's say u, which is y1, y2, y3, lambda times u plus v should be equal to lambda times u plus lambda times v. Let's check that. So u plus v. Well, what is this? Well, first I have these two vectors added up. This vector plus this vector. All right. Okay. Now, what is this? How would you add two vectors? Well, we are taught to add these vectors just component-wise. So, x1 plus y1, x2 plus y2, x3 plus y2. Okay, now I have this scalar product of the vector with this vector. How this is defined? Well, you just multiply each component by the scalar. All right. And then what we can do? Well, each component has this term, but these are just real numbers. And in real numbers, we can distribute multiplication over addition. So this product is just lambda times x1 plus lambda times y1. This is the property of real numbers, not vector space. Okay, I'm just using the property of real numbers that this is equal to this gadget. And similarly with this one, I had plus here. Sorry, right? Plus. I copied wrong. Now, what is this? This is just x times, no, lambda times x2 plus lambda times y2. And this is lambda times x3, lambda times y2. All right. And then we do what? Well, this is similar to what we had over here. Right, this looks like sum of two vectors. Which two vectors? Well, that is just lambda x1, lambda x2, lambda x3, plus lambda y1, lambda y2, lambda y3, right? Now I am using the property of vector space, okay? This is how we add two vectors. And then finally, I can take this constant out because this is nothing but the multiple lambda times the vector x1, x2, x3, right? x1, x2, x3. And this is lambda times y1, y2, y3. So this is just lambda times u, no, v plus lambda times u. So what we have seen is that lambda times u plus v is just lambda u times lambda v. Okay. So this is just this property over here. Okay, this property. We showed that with this definition of vector addition and scalar multiplication, our claimed vector space satisfies this condition and this condition. Now we have to check the remaining two conditions. All right, that's kind of easy. Now, lambda times, sorry, 1 times b. 1 times b is just, let's say, x1, x2, x3. How would you multiply a scalar with a vector? Well, you just multiply each entry by that scalar. But, these are real numbers. This is the one in the real number system. 1 times any real number is just that real number. So we get just 1. Okay. So 1 times b is really. What about 0 times b? Well, 0 times the vector x1, x2, x3. By definition, this is just 0 times x1, 0 times x2, and 0 times x3. But in the real number system, if you multiply a real number by 0, you just get the 0 real number. So this is 0, 0, 0. So these are the zeros of the real number system, but this is just our 0 vector. Okay? So 0 times b is just 0. This 0 is the 0 of the real number system. This is the 0 of R3. Okay, the 0 vector. Okay. I will not go into this much detail in other examples, maybe in some of them, but I didn't write down something unnecessary here. Okay, one should just go through all the steps to show that R3 with this operations of vector addition and scalar multiplication is a vector space. The proof of that is, should contain all these steps. If you think that these are, unnecessary, then you are missing something. Okay, you should go back and study the definitions and so on. Okay. Yani bu işlemlerin anlamsız olduğunu düşünüyorsanız o zaman vektör uzayı nedir konusunda sıkıntınız var demek. Tamam mı? Buradaki hiçbir adım gereksiz değil. Trivial olabilir, basit olabilir ama gereksiz değil. Ama bundan sonra tabii ki bu kadar detaylı yapmayacağım. Tamam mı? So. Which one? This one. Yani şuradan mı?
Evet.
Buradan buraya.
Onu bekliyoruz biz özellikle.
Evet. Just think of this way. How would you add these two vectors?
Yok, yani bir öncekinden ama.
Tamam. Yani buna eşitliğini soruyoruz değil mi?
Evet.
Tamam. Şuradan başlayalım. How would you add these two vectors? Well, you add them component wise. So this plus this one. This plus this one, which is this gadget, and then this plus this one, which is this gadget. Yani tanımı şöyle yapıyorum. Bu iki vektörün toplamın olarak tanımlanacak. O yüzden bu buna eşit. Değil mi? This is how we define vectors. Right? How do you add two vectors? You add them component-wise. Okay. Any questions? Dediğim gibi anlamsız geliyorsa size veya gereksiz hoca gereksiz işler yapıyor diye düşünüyorsanız yani oturup bir daha çalışmanız lazım. Tamam mı? Buradaki her adım gerekli. Peki Okay, that was example 0. This is example 1. The set of complex numbers is a vector field over the field of real numbers. Okay. So our vector space is the set of complex numbers. What we mean by that? We mean things like this, right? A plus ib, A and B are real numbers. This is my vector space. So I should tell you how I add two complex numbers. Well, we know already how to add two complex numbers. If Z1 is this, let's say, and Z2, A2, are B2. If these are two complex numbers, okay, then how would you add this up? Now I give you the definition, okay? I can define addition in a different way, but here you'll just take the usual definition of complex numbers. And what's that? So A1 plus I times B1 plus A2 plus I times B2. My definition of complex numbers is the following. I add real parts, so A1 plus A2, and then I times the imaginary parts, B1 plus B2. This is my definition of addition of complex numbers. All right, so this is the addition. What about scalar multiplication? Scalar multiplication of what? Of vectors with scalars. Vectors are complex numbers, scalars are real numbers. So I take the scalar and the vector. Vector is a complex number, and I will tell you how we would multiply these two. So lambda times z. Well, lambda times z is defined as follows. If z is, let's say, a times ib, then I define it this way. I multiply real part by lambda and imaginary part by lambda. Here, this multiplication is the multiplication of two real numbers. Lambda is a real number, a is a real number, and I'll just multiply two real numbers. And the same thing here. And here, again, this is addition of two real numbers. This is the addition of two real numbers. This addition and this addition are different, right? This is the addition of vectors. This is the addition of real numbers. They are different operations, but they are compatible, okay, in this sense. Sure. This is the definition. So here I didn't do anything. I don't claim anything. Lambda times z. Z is just this thing. But here I make a definition. For me, this thing is just this. Okay, I define this product or scalar multiplication as this object. Okay, I could have defined in a different way, but maybe in that case it may not be a vector space. Okay. Yani işlemi istediğim gibi tarif edebilirim. Koşulları sağladığı sürece de vektör uzayı olur. Ama yani şu anda mesela başka bir şey tarif edeyim de orada vektör uzayı olsun diyebileceğim bir şey aklıma gelmiyor. Yani. Başka bir vektör uzayı yapısı kurmak kolay olmayabilir. Okay. Now we have to check all the properties of for being a vector space. What are they? So complex numbers with the addition should be an abelian group. Right, so the and there is this operation, and this should be an abelian group. So if you have two complex numbers, let's say A1, IB1, addition of these two is defined here, and it should be an abelian group. In other words, Z1 plus Z2 should be same as Z2 plus Z1. But what is this? This is by definition A1 plus A2 plus I times B1 plus B2. Addition of real numbers is commutative. I can write it this way: A2 plus A1, I times B2 plus B1. And then write this as follows, again using the definition: A2 plus IB2 plus A1 plus IB1, right? And this is just Z2, Z1. So the addition operation is really commutative. Here I am using the commutativity of addition operation of real numbers. What is the zero element of this abelian group? The zero element here is just the zero real complex numbers. So it is 0 times I times 0. So both real and imaginary parts are 0. Then we should check all the properties are satisfied. Let me just do one of them. For example, lambda and mu are real numbers, and z is a complex number. We should check this, right? Lambda plus mu times z is lambda times z plus mu times z. Let's see if this is true. Lambda plus mu and z, let's say, has real and imaginary parts as a and b. How did we define scalar multiplication? Well, we define it this way: we multiply the real part with the scalar, and we multiply the imaginary part by the scalar. Now, these are all real numbers, and in real number system, this will be just equal to lambda times a, mu times a, plus, and again, these are real numbers. I can just write it this way. And then we do what? Well, this is just the sum of two complex numbers, namely lambda times a plus I times lambda times b. And so I take this one and this one, and then mu times a plus I mu b, right? This is the definition of two complex numbers, right? How do I add two complex numbers? I add real parts, and then I add imaginary. Okay, and what is this gadget? Let me just write over here. This thing is just lambda times a plus ib plus, this is just mu times a plus ib, and this is equal to lambda z plus mu z. So this thing is equal to lambda z plus mu z. Yes.
I could distribute I over its lambda b plus.
Well, we don't have anything like that. We didn't define. I mean.
Oh, I got it by addition.
Yeah.
Okay.
Yani şöyle bir şey yapıyoruz. Kurallar yazıyoruz. Nasıl toplayacağız? Nasıl çarpacağız? Sonra da o kurallara riayet ediyoruz. Yani o kuralları bozmuyoruz hesap yaparken. O yazdığımız, tarif ettiğimiz kurallar gereğince bu işlemleri yapabiliyorsak o zaman diyoruz ki bu vektör uzayı. Yapamazsak o zaman vektör uzayı olmaz. Tek tarif etme yolu bu mu? Değil. İleride onu göreceğiz. All right. So I will not go over other details for this example. That complex numbers is a vector space over real numbers. Of course, complex numbers has an extra operation. In complex numbers, we can also multiply vectors, right? Because vectors are just complex numbers, and we know how to multiply complex numbers. So we know also we have an extra operation, which doesn't exist in an arbitrary vector space. But considered as a vector space over R, we don't care about, at this point, this multiplication of complex numbers, okay? It is not a part of being a vector space over R. It is an extra operation, and actually it is very useful, you will see that. But at this point, we are not interested in that. Okay. Another example of vector space is this. Example 2. Right, that was example 1, example 2. Consider the set of all three-dimensional vectors V in R3. R3 is itself is a vector space over R that are which are perpendicular to a given vector A, which is not 0. So V is this. It is vectors, so V in R3, so that A and B are perpendicular to each other. Perpendicular to each other means their scalar product is 0. Okay, so if let's say A is the vector A1, A2, A3, and B is the vector, let's say, okay, let me use just X, Y, Z for simplicity. This perpendicular, being perpendicular condition is this: A cross A dot B is 0, but just A1, A2, A3, dot product V1, V2, V3. So what is this? This is A1, V1, A2, V2, A3, V3 is 0. So V is the following gadget. Let me just try to draw it. So we have some, let's say, vector. Okay. Önce vektör uzayını çizeyim de ondan sonra çizelim. Let's say our object is something like this. The set of all vectors perpendicular to this gadget. Okay, let's say A. So A is a vector in R3, X, Y, Z, and it is perpendicular to the plane, this digit. So, so it's like, you know, if you have a vector, suppose this is the vector A, V is all the vectors that are perpendicular to this vector. What is that? Well, it is just this plane, right? Admitting this as its normal vector. Okay. Now we claim that this is a vector space also over R. I have to tell you what are the operations. The operations okay. Şey yazmadım zaten, claim'i yazmadım. B is a vector space or R with the following, with the operations inherited from R2. We know that R3 is already a vector space over R, right? And V is a subset of R3. So if I take two vectors here, then they are vectors in R3 and I know how to add them up. If I take a vector in V, then it's a vector in R3 and I know how to multiply it with a scalar. But we should be careful that, you know, when I take two vectors here, the sum should be over here, right? Otherwise, that wouldn't be an operation on V. If addition is an operation on V, this is what we are claiming, then sum of two vectors arbitrarily chosen from this set should lie in the set, right? Because, you know, this plus operation, I claimed that this is an operation in R3. So then I will take two vectors, add them up, you get a third vector. I claim the following. If I restrict this operation to V cross V, in other words, if I take two vectors from V, then the sum also is a vector here. Otherwise, that wouldn't be an operation on V. Değil mi? Yani grup işlemi olması için we are claiming that this is an abelian group. For that, for this thing to be an abelian group, this should be an operation. An operation does what? Takes two elements of the set and sends it to a third element. So if I take two elements from this, then I should end up with an element here. Okay? So, we need to prove that sum of two vectors in V is another vector in V. Okay, for plus to give an operation and on V, we must show that if UV are in V, then U plus V is in V. So that this digit will be an abelian subgroup of R3 with plus, right? This is an abelian group, we know that, and this is an abelian subgroup. Şeyi gördünüz değil mi? Subgroup nedir? 116'da mı? Okay. So let's check whether this is correct. Bir zaman doldu mu? Evet dolmuş. Okay, let's have a break. After the break, I'll continue. 5 dakika geç bıraktım. 5 dakika geç gelebilirsiniz. Tamam.